Okay, you ready for some football? Anybody catch any games this weekend?
Unfortunately.
Yeah. Thank you again for inviting us to speak to you guys today at the ASCE Dallas branch. Once again, I'm John Aniol, Vice President of Dallas Office of Thornton Tomasetti. Today we'll talk to you about the Minnesota Vikings new stadium, Minnesota Multipurpose Stadium. And of course, it all begins with the team. The owner for the project is the Minnesota Sports Authority, and led by the primary tenant, the Minnesota Vikings. It'll be a multi-purpose venue, but the Vikings will be, of course, the primary tenant. HKS is the architect in Dallas, led by Bryan Tyson. And, of course, Thornton Tomasetti is serving as structural engineer as well as skin consulting and mechanization consultant as well as connection design engineer for the project. It's of course the structural engineering team is a 20-person team. The roof is being led in Dallas, and the seating bowl is being led in the Kansas City office. And even our company CEO Tom Scarangello is the principal in charge of the project, and Steve Hausmeister, project director from Kansas City. And just quickly today, of course, we'll give you just a shortened version of the presentation because we just have 30 minutes, but we're going to move pretty fast and just quickly, briefly on the schedule. The design schedule is 18 months. We started in November 2012, and we issued construction documents in May 2014. Construction duration is 33 months. They started construction November 2013. Of course, it's going to open in July 2016. And the roof erection is 16 months. And now, quickly, just a brief overview of the site. It's I don't know if you know Minneapolis, downtown Minneapolis, but it's adjacent to the Mississippi River, and the downtown CBD is just to the west. This is the project right here. It's a primary ridge of the roof that's oriented in the northwest direction. Mississippi River is over here on the east. And just an aerial view, you can see the transparent roof on the south of the roof, and of course the tall buildings downtown district here on the west, Mississippi River. Just a quick a view from the West Plaza. There's 5 operable doors here on the West Plaza that allows a panoramic view, both from the West Plaza onto the field and within in the stadium a view of the skyline. And as you can see from this rendering, this is the south translucent ETFE roof that we'll talk more about in a minute, and then this is the West Plaza that we were just viewing. So it is a multi-purpose venue. It'll be home to NCAA Final Four and, of course, the Super Bowl, I believe, in 2019. It seats 72,000 seats. It's 1.6 million square feet. There's roughly 160 suites. Comparably, Cowboy Stadium was 3 million square feet and over 260 suites. So it is somewhat smaller than, for example, a Cowboy Stadium. But the total project cost is $975 million. Construction value is $750 million. It is very expensive to build in Minneapolis. The labor rates for the roof erection, the labor rates are about twice what they are here in Dallas. So it's an expensive place to build, and a challenging place to build, of course, with the snow loads and that sort of thing. But we like to think of it as creative, monumental solutions that were met by leveraging technology as well as utilizing the firm's sports and long span experience. And just another rendering from the northwest. Of course, as you can tell, the overall project lacked symmetry, which was a challenge, but that was one of the distinctive forms, and architect HKS that developed the overall form. Here's some more renderings of the overall roof form. You get an idea of the lack of symmetry, but what adds to the distinctive nature of the project. And of course, the transverse section, as you can see here, this is the main ridge truss down the middle, and then the west plaza, and what we call the queen post trusses that span from the ridge truss to the seating ring beam, upper seating deck. And then now the longitudinal section, which is the primary roof element, the ridge truss that's over 950 feet long from tip to tip, and then it spans over 850 feet from the base of the abutment to the base of the abutment at the main concourse level. Of course, one of the challenges building in Minnesota is the snow load. So with collaboration with HKS, we decided to pitch the roof 14 degrees and 17 degrees that subsequently gave us a significant reduction in our roof snow loads. But as you can see from this image, that both the south roof and the north roof have a slope, as well as a ridge. And now materials. There's two primary materials on the roof. Of course, structural steel, but as far as cladding materials, the south roof is ETFE material, which is over 240,000 square feet of translucent material, which is highlighted in the blue area, which is on the south side. It's clear, transparent. And then traditional steel roof deck on the north with a PVC membrane roof. There's, of course, the hard deck. And then, of course, the ETFE. ETFE, it's different than the PTFE, which is on Cowboy Stadium and, say, on Reliant Stadium. This is a clear, translucent material. It's a polymer film rather than the PTFE, which is a Teflon-coated fiberglass. We'll get into more details of this in a minute, but it's a pillow system, a three-ply pillow system that's air inflated that creates these pillows that will give the appearance. This is a similar project in New Zealand, but so when the stadium opens, it'll be one of the first. Of course, it'll be the first NFL stadium to utilize this ETFE material on the roof application. And then moving on to the roof framing. Of course, the hierarchy of the roof starts with the purlins, which are steel beams, W30 steel beams on 10-foot centers that span 55 feet. And then we have the secondary trusses that are 10 feet deep that span 135 feet. And they're, of course, 55 feet on center. And then the queen post trusses that span from the ridge truss to the concrete ring beam. And then the ridge truss itself, it's comprised primarily of grade 65 steel that like I said, spans 850 feet from abutment to abutment and is over 900 feet long from along the ridge. And this, of course, is comprised of, like I said, it's grade 65 steel. There's over 11,000 tons of steel in the roof. The roof is a very light roof for comparable loading. Due to the configuration of it and the spans, we're able to reduce the spans, and we're also able to reduce the snow loads that we'll talk more in a minute. But like I said, it's the ridge truss. The total roof tonnage is 11,000 tons, over 3,500 tons of grade 65 steel, ASTM A913. And Lejeune Steel is the primary steel fabricator in Minneapolis, and Danny's is the erector, and Mortensen is the general contractor. Of course, RWDI was the wind tunnel consultant. And here's a better view of the ridge truss. There's members in the ridge truss that are comprised of, the chords are comprised of W36 members. The heaviest member in the top chord of the truss is W36 by 853. Some of the smaller ranges down to W36 by 150, but most of the members are in the 300 pound per foot range. And then the inner columns, as you can see, slope at a 45-degree angle. Those are also W36 chord members. And the ridge truss itself is a box truss that's 15 feet wide and as deep as 55 feet in the middle and tapers to 15 feet at the end. And similarly, the inner columns are 15 feet wide and 20 feet deep, and as you can see, taper. And of course, one important aspect of the ridge truss is to make an economical design is to keep the slenderness ratio to a KLVR less than 30 in order to utilize the grade 65 steel. So we were able to keep the slenderness ratio with an average of 31, which allowed us a 27% increase in yield strength compared to grade 50 steel. And as you can see on this histogram, this is a plot of the difference between grade 50 steel and grade 65 steel, and then we were able to capture this 27% increase in yield and stay in the inelastic region. Of course, one important aspect of long span roof design is stability bracing, and this played an important role both from a global aspect as well as a individual element aspect, and we use these three publications for extensively for design criteria as well as the evaluation of overall stability and element stability for the project. And just more on the behavior of the ridge truss. It's a combination of arch and beam behavior, both P over A and M over S, to get, with compression loads that are on the order of 6,500 kips in the ridge truss. And as you can see, the red highlights the ridge truss and the east A-frame, what we call the east A-frame at the end. Of course, a lot of this geometry was dictated by the overall roof form. And then moving on to the buttress foundation where the inner column of the ridge truss lands. This is a 10-foot by 10-foot concrete column that's at a 45-degree angle that's terminated with a mat foundation that's into bedrock at just below the event level. This happens to be a built-up member where as you may recall, the inner column that's coming down and tapers into this one section. And there's a photo of the actual built-up column in the fabrication shop. And now the queen post trusses, which are these elements that span from the ridge truss to the ring beam. These elements are box truss as well. It's 10 feet wide and 10 feet deep, and then the tension cord is as deep as 55 feet deep on the south and 35 on the north. These trusses span up to 400 feet and create the economical primary element that also is part of the lateral load resisting system. And as we spoke before, the secondary trusses that are 10 feet deep and span 135 feet. And the purlins, which are W30, W24 beams. And more on the ETFE, as you may note that the roof orientation of the framing, we oriented it down the fall line of the roof to match the pillow alignment. So when the snow would slide off the roof, it would be down the fall line because these pillows create this ridge and valley system. So in order for the snow to shed off the roof, the pillows and the roof framing was oriented down the fall line of the roof. As you can see, the primary load path for the roof structure comprised of the ridge truss, the queen post trusses and this concrete ream beam, which is a 4 foot by 4 foot concrete ream beam at the top of the seating bowl that creates this horseshoe element that goes around the perimeter of the roof. And the ring beam is supported by 6 foot square concrete columns that are there's columns roughly at each bowl grid at every 50 feet on center approximately. There's just a plan view of the overall roof lateral load path system as I was describing the concrete ring beam. And then lastly, we do have 5 operable doors. Thornton Tomasetti was the mechanization consultant for the project. There's 5 operable doors that are 55 feet wide and 75 feet tall that taper from 75 feet up to 95 feet, and they're driven by a hydraulic system. This will allow an open panoramic view both inside and outside of the stadium, as well as allowing spectators to congregate on the West Plaza and quickly move in and out of the stadium. There's just a isometric of the operable doors. Now I'll hand it over to Bryan to talk about advanced modeling.
Thank you, John. So my job on the project was I was the lead design engineer for all of the modeling aspects of it. And one of the things that we employed real early on in the project for the schematic and pre-schematic phases was we employed both Rhino as well as a plugin called Grasshopper, which allowed us to very quickly manipulate the geometry of the stadium to match ever-evolving changes that the architect had. And then from there, we were able to then export this geometry from Rhino into SAP to be able to analyze the structure, and then eventually from there into our BIM modeling package for Revit. And this made us able to very easily adapt changes. In some cases, we could have a week to a week and a half to produce a completely new set of BIM model drawings off of a change in the general architecture of the structure. And here is a shot. This is an example of, where's the mouse? There's the mouse. So this is a image of how we can easily adapt the structure within Grasshopper. So we can change the floor plans, we can change the height of the building. All of this is done in real time. And then from there, we can then have plugins, as you see right here, that analyze the tributary areas of the floor slabs. And then we can export this into SAP, be able to analyze it, bring it back into Rhino, and then from here we could even show if there's any failing members, as you'll see. Kind of hard to see, but some red members in there were failing members. So then we will know what we need to change. And we can do all of this real time and have a much faster turnaround than typically would happen. And then from this, we can export it into Excel, and then we're able to bring it right into Revit. And then when in Revit, we've already got a building with almost all of its geometry already incorporated, and it's very little work that has to be done after this when you're in the early schematic phases of the project. And so here you can see the end result of that analysis. So it's a very fast process, and it helps to go through a lot of different schemes very quickly in a project. This is a general layout of the Grasshopper arrangement. What Grasshopper does within Rhino is it allows you to manipulate large amounts of data, matrices and arrays, and it's a visual programming language, so you can easily just draw lines to connect across what you want to model. So we bring in from Revit the architectural background for the skin framing, and then within Grasshopper, we will then able to constrain our structural framing to that architectural skin, and then from there we could then export all of the data into SAP and be able to analyze it. So for the loading, we worked with RWDI to do the the wind loading on the primary as well as components and cladding loads, and they did a wind tunnel model, as you can see in the lower left corner, and then the top is one of the examples of the wind pressure maps that they gave us. And then this is an example here also of a map from the south half of the roof as well as the southern facade with the wind loadings. And we worked with RWDI real early on to determine the best way to create a zoned region on the roof. And we had 263 different regions. And we worked with them on this because each one of these regions corresponds to a pressure tap in the wind tunnel model. And then all they had to do was give us their Excel data. We could easily incorporate that Excel data straight into SAP, and we automatically had all of our wind loads applied to the structure. And this is an example here of all of the area elements with one of our wind load cases. And in some cases, the components and cladding loads were upwards of about 75 PSF, as you can see in the left side, the west portion of the building there. Yes, it was pretty high. RWDI was also employed to conduct the snow load studies on the roof. This image here was from a pre-concept that they had done a few years earlier, where the intent at first was to try and keep all of the snow on the roof. But we found that was very infeasible because some of these snow loads were getting upwards of 380 PSF of snow load, and just we couldn't handle those kind of loads. So we decided, instead of trying to hold all the snow on the roof, to just let it fall off the roof and fall into gutters on the side of the roof. And that's what we ended up doing instead. And so part of the snow load design criteria is you have the CS value. It's a roof slope factor. And this is an example where we used Rhino and Grasshopper again to be able to determine the slope of the roof. And then from there, we were able to see what the slope factor would be. And so we could work with HKS directly on this, and we could determine how changing the height of the building will then affect the snow load factors on the roof, and find that optimum balance there between reducing the snow loads and keeping the cost of the building down. If we make the building too tall, it just gets too expensive. In this case, we found a decent balance at about 75 to 85% of the ground snow load value was what we used in the early concept stages of the project to design the roof to. And then after we did these studies, we then went back with our WDI, and they created a finite area model of the roof. And what they're able to do is they went back to past historical data for the snow loading. And back in, it was the winter of 81 to 82, they found to be some of the worst snow loads that were up in that region. And their finite element model would take their wind load data as well as the snowfall data, and then from there they could create a map, like you see in the lower right corner, of the snow load distribution throughout the roof. And then in the end, we got snow loads down to between 23 and 33 PSF. So we went from 380 PSF holding it on the roof down to 33 PSF if we just let it fall off the roof. So one of the challenges, though, with having that much snow sliding off the roof is how do you divert it down into those lower gutters and not just have it fall off the roof and take half the roof with it. And that's where we designed the snow barrier fence. So we had the purlins were sticking out beyond the facade of the building. And then we had this snow barrier fence that consisted of these metal posts, and then a snow cable fence attached to those posts. And that way we can have the snow hit that barrier, and then it would be able to fall straight down into the lower catchment gutters and not fall off the building. In this case, we also had some very high loads, though, to deal with. We were upwards of over 5,000 pounds per foot of snow load was on this barrier fence. And this was actually the idea for the snow barrier fence. This is what they use on the sides of mountains to catch avalanches. And it's the same concept that we're employing on the roof of the stadium. So we have a strong post, and in between those posts is a pre-stressed cable net fence to be able to divert the snow down into the gutter. Another study that we had to look at, and this was back in Grasshopper again, is the snow trajectory study. We wanted to optimize the depth of our deflector system to be able to make sure that the snow is either going to hit the barrier and then go down, or the snow at low velocities will just fall off the building to the lower catchment gutters. But what we didn't want to have is a region in there where the snow could either miss the barrier and miss the lower gutter. And so that's when we went back into Grasshopper and created a snow trajectory study to be able to see if there's any areas of snow that could miss both the deflector and the gutters. And then we knew that we would have to make our deflector slightly deeper in those areas. For the analysis, we used a lot of just your typical cases. We did the service drift and the strength case. Both of them were full nonlinear analysis, and we designed through the AISC and ACI's stability designs. And then we also used the fairly newly released Design Guide 28, a stability design for steel buildings as well, to account for torsional bracing and other factors like that. Another thing we looked into for the design of the ridge truss is to optimize the robustness using a global buckling analysis. So with running a global buckling, we're able to determine if there's any weak links within the ridge truss members, and we knew we would increase those to give us a buckling factor. Usually we try to be about 3.5 times above our service load cases. And we also ran a modal analysis case, which was given back to RWDI, which they were able to use to determine the aerodynamic effects and if any increased loads would be caused from the modal forces when under wind loads. We also looked at stage direction analysis as well as a steel deck stress analysis. This is an example here of our SAP model. So the overall model had a little over 20,000 elements, with about 15,000 of those in the roof alone, and then the remaining 6,000 were down in the concrete bowl. We had about 10,000 nodes, 75 load combinations, and then 210 or 65 load cases and 210 load combinations, with our controlling case being our full snow load case as well. And this is a view. We had 1,200 area elements throughout the roof too. And you could see on the lower right of the corner, there's that gap there. That gap was the separation between the outer fence or outer facade of the building and where the roof gutter is, and then the upper deflector above it. This is just a shot of one of our modal cases. So we use this modal information to give to RWDI so that they can analyze any increased effect that the modal induced loading would cause from the snow loads. And this was an example of a report that we gave to RWDI as well, summarizing all of our mode shapes that were under 1.5 hertz. And we broke them down by both global loads and local modes, so that they knew if it was a local mode, it wouldn't have any effect on the overall roof. This here's our first mode, was a east-west lateral translation of the ridge truss, where the outer ring beams to the far north and far south were staying place, and the ridge truss itself was just moving east and west. And that was at about 5.8 hertz, or 0.58 hertz. And this is our second mode case, where it was just the west side of the structure was moving north and south, which was at about 0.69 hertz. Another thing that Thornton Tomasetti was hired to do is the connection design for all of the stadium. And this allowed a real seamless transition between us on the design side and the connection design and modeling team as well. That way, when they make changes to a connection, say an axial connection had to end up taking moment, they could easily get back with us. We could update our model. It gives them more accurate forces and a lot faster than if you were to traditionally go through a separate connection company to design them all. And this here is one of the examples. This is a connection in the ridge truss at a panel point. And the image on the left there is the drawn connection detail. And then the image on the right is the modeled connection within Tekla as well. So all the shim plates, nuts, bolts, everything is in there. And what we're then able to do is hand this Tekla model off to the steel fabricators, and all they have to do is go straight into producing their shop drawings. They don't have to model anything additional in it. They just produce shop drawings, send it to us. We can then use the Tekla model again to back check all their shop drawings. And this is an overall view of the main ridge truss on the west side with the column coming up. The catwalks were modeled in there and everything, although the catwalks are a little hard to see. And then this is an image of what that piece currently looks like on the ground. It's currently being fabricated, and it'll be erected here in, I think, a couple months, I believe. So, and with that, if you have any questions, I'd like to open up the floor.